Okay, so this is the lab on standing waves, and we're going to produce some standing waves that you can see and some standing waves that you can hear. So let's talk about the standing waves that you can see. We're going to produce the standing waves with a vibrator. This is the vibrator, and this is the string that's going to be vibrating. So this is a vibrating string experiment. We'll have this strung out, and you'll see this in the lab when we look at the procedure, which is pretty simple. So this plugs into a variac, a variable voltage transformer, so that we can not vibrate it at too violent a rate and cause all kinds of crazy things to happen. So we'll have the variacs adjusted for you, hopefully before you get there, and so you just have to turn it on. And it'll be set at something like 60 or 80 volts instead of 120 volts. So we have a vibrating string. So that the setup, there'll be one of our smart pulleys over here, and there'll be the little vibrator that we just took a look at, and there'll be a string in between those. And you'll have your weight pan that you had used a lot last semester, and you're going to put weights on it. And the weights, of course, provide a gravitational force, which is going to produce, we'll just call it big T, tension in the string. The force stretching the spring. So this gets plugged into the wall. It vibrates. There's a little flap that vibrates up and down. It's plugged into the 60 hertz wall, but every time, here's one cycle. That's a 60th of a second. You know that from your work with the cathode ray tubes and oscilloscopes. But every time this reaches a maximum, the voltage goes up to its maximum, it causes that little tab to be pulled in. So it's actually 120 hertz. So the frequency is 120 hertz. I have to tell you my story about hertz. Okay, why is the unit for frequency hertz? This starts back in the 1880s when bicycles became very popular. That is, modern bicycles became very popular. So the penny farthing bicycles with a big front wheel and a little bitty back wheel, which were almost impossible to get on without falling over. So we have the modern bicycle. When there was a bicycling craze from the 1880s through the 1890s, and people bought hundreds and hundreds, thousands, millions of bicycles. The world's biggest manufacturer of bicycles was a factory run by Heinrich Hertz. Okay, and so he would make bicycles, and at the maximum output of the Hertz factory, he would make one cycle every second. That was quite the production. So we have 1 hertz is 1 cycle per second. And of course that's short for bicycle. Well, if you believe that, I have this bridge in Brooklyn to sell you. But anyway, so a hertz is 1 cycle per second. That's not exactly really why we have it named after Hertz. Heinrich Hertz was a very famous physicist who lived in the 1800s, late 1800s, did some really neat experiments with electromagnetic waves and so forth, which we'll be talking about later. So enough funny business. So standing waves. Standing waves are actually traveling waves that look like they're standing. So, I mean, one standing wave you might notice is such as this. That would be a standing wave. But these are actually traveling waves. They're traveling back and forth on that string at hundreds of meters per second, and it's really hard to see that. So this would be a traveling wave, by the way. This is a Royal traveling wave. Okay. And this is a microwave. Did you see that? That's a microwave. So you know all about waves now, in case you haven't gotten to them in the lecture yet. So we're talking about standing waves, which are traveling waves that are reflecting back and forth. So here's this. Let me just draw a kind of a wall here. The little vibrator doesn't vibrate at a big enough amplitude to worry about that, so we're going to call that like a 0 amplitude. And we have a word for that. It's called node. Okay, and then here's this smart pulley with the pan hanging down. So here's this nice long, 1.5 meters long length, which you're going to need to measure. So we'll have a couple meter sticks put together so you can measure that length. That's really the only time you have to measure any length, is the actual length from where the vibrator, the end of the vibrator is, where the strings tie the vibrator, and the very top of the pulley where it stops being able to vibrate at the very top. So this is the length from here to the top of the pulley. Okay, so what's happening is this is a sinusoidal vibration, and it's going to produce a bunch of sine waves. So produce a bunch of sine waves that are going down that string, and then going to hit here and have, this is a node, we'll call it big N for a node. This is another node, a big N for a node. And the waves are going to hit there, and if you put the right amount of mass here, put the right tension in that string, you're going to have a situation where when these waves get over to the pulley, they're going to have a zero amplitude. And they're going to reflect back, and they're going to come back here and have a zero amplitude and go back and forth very rapidly at a pretty high speed, many hundreds of meters, or roughly 100 meters per second. Okay, so the wave that can be produced, standing wave that can be produced, that's the one that's simplest, is a wave that has a node here and has what's called an antinode in the middle, and it bounces back over this way. So here's the antinode again. So this antinode appears at half the length of the string. So this is called the fundamental frequency, or the first harmonic. Let's call it the first harmonic. It gives us a nice number to work with. You know what the wavelength of a sine wave is, and so pretty obviously that certain part of a sine wave is this part, which means it's a half a wavelength of a sine wave. So this is a half a wavelength long. So L is a half a wavelength here for the first harmonic. Again, all you need to measure is the length. You don't need to measure half the length. You can just divide by 2. That's easy enough. So the fundamental frequency, or the first harmonic, is where the length of the string is exactly a half wavelength. So your job is to put just the right amount of mass on this, and you might have to go down to the nearest gram, and so that you get the biggest amplitude. And that's called resonance. So we're looking for resonance where this string vibrates with the biggest amplitude. This is the amplitude Y here. And that's what you're looking for. And when you have that, you have this condition, and the string length is a half a wavelength. We're not going to do that because it takes so much weight here to do that, that you're in danger of busting the string or making this little vibrator not be able to vibrate because there's too much tension in the string. So we're not going to start there. We're going to start with the second harmonic. And I'm sure you know what it looks like. Second harmonic would be where the string vibrates. Those should be equal. In 2 nodes, there should be a node in the middle, a node on each end, and 2 antinodes. So 2 humps, so to speak, is the second harmonic. That's a nice, easy way to remember what harmonics mean in terms of the shape of the string. Okay, so this wave's going back and forth, reflecting back and forth, and if you put the right amount of mass on that platform, you'll get the biggest amplitude here, and that's what you want. And of course, the third harmonic would look like this. There's the pulley, there's the vibrator, and of course the length of the string is 1.5 is 3/2 of a wavelength. So this is 1 wavelength. L is 1 wavelength. For the fundamental, L is a half wavelength. We can call those L1 and L2 and L3 if you want, or whatever. So this is the first harmonic, second harmonic, and third harmonic. You kind of see a formula coming out here. That is, if we change this number upstairs to N, where N is any harmonic you want, N would be 1, would be 2, would be 3 here. This is 2 over 2, 1 over 2, 2 over 2, 3 over 2. So the length of the string is related to the harmonic by this formula here, n lambda over 2. So the fourth harmonic, the string would be 2 wavelengths long, one wavelength, 3/2 a wavelength, next one is 2 wavelengths long. So this is a very simple little formula, and that's the formula that you're going to work backwards to find the velocity. Okay, so let's put this formula down here. The velocity of the nth, the length of the nth harmonic is n times lambda over 2. That's our working formula, where all we need to do is measure the full length of the string, and we can see how many. You need to count how many antinodes, how many humps there are in the string. So if you got 9 humps, then then we're talking about the 9th harmonic. The number of humps, 1, 2, 3, 4, and so forth, is the harmonic number, and that leads again to this formula as we saw earlier. So in a string like this is given by the square root of the tension in the string, which we know is the weight of the weight on that pan, divided by mu. Mu is called the linear mass density, and of course it makes sense that different size strings, ropes, fine strings, and little sewing strings or whatever not you have, it's going to produce. There's going to be a different velocity for all those different quantities, and the thicker the string is, the smaller the velocity, which kind of makes sense also. That's why this is downstairs. So you need to also measure the length of the string, and you need to measure the linear mass density of this particular string. Now, don't take the apparatus apart and take the string over to measure the mass on a balance, because there's a knot here and there's a knot here, and that's not very handy. So don't do that. We have a piece of string that's a meter long, a little bit less than a meter long, 96 centimeters or whatever it is, and just measure that length of string and find out its mass, because the linear mass density, because you're dividing the mass by the length, is the same for any length of string. So don't take the string apart. Take that sample piece of string, stretch it out fairly tight, because this is fairly tight thanks to the weight you have on the string, and measure or calculate the linear mass density, which is what goes into that formula there. You can calculate the velocity using this expression. So you want to see that the velocity is, of course, different for different tensions, and so you're going to get 9 different velocities for the second through the 9th harmonic. Let's try to go through the 9th harmonic. It gets a little ragged at the end with all these little bitty bumps, and you kind of find a hard time counting them and finding them, but you'll get better at it. So that's the first half of the experiment for standing waves that you can see. Okay, so for all waves, electromagnetic waves that you'll be talking about, standing waves, waves in a string, water waves, any kind of wave, except the waves that I've made up earlier in my jest, we have a formula that relates the frequency and the wavelength to the velocity of the wave. The frequency is in cycles per second. The wavelength is in meters, and of course, cycles is just a kind of a placeholder. It's not really a unit, and so we get meters per second if we do a little unit analysis here. So this is the velocity from measuring your frequency in hertz and your length in meters. You get the velocity. So the velocity is all wave velocities here. We're talking in particular is the frequency. Again, the frequency is 120 hertz, right? Times the wavelength. So from this formula, you can get the velocity for each harmonic, and from this formula, you can get the velocity for each harmonic. So those are the things you want to compare, see how well you do. Second half of this experiment is standing wave experiment is standing waves in an air column as opposed to standing waves in the string. So these are the standing waves you can hear. So again, when you have resonance, when you have the standing wave with nodes on each end, or like we had here, it's not quite the same for a wave in an air column. We'll talk about that in a minute. But you're going to get the loudest sound instead of the biggest amplitude of the string. So we're going to be listening for the loudest sound. And it could be a little confusing if we have 4 groups doing the same experiment using the same frequency. So we'll tune the frequency generators to slightly different frequencies so that you know what your sound sounds like, and you know what your neighbor's sound sounds like, and you know which one's which. So we'll use frequencies of about 1,000 hertz, give or take 100 or so. So they sound pretty similar, and they give you a nice answer for the wavelength. Okay, so here's this tube. It's a plexiglass tube. It's called Kunst's tube, and you're going to produce some standing waves that you can't see them, but you can hear them. Okay, to do that, we have a piston on a rod. The length that you're going to be measuring is between the end of the tube, which is open, and where this piston is. And over here we have a little speaker attached to a frequency generator, such as you've seen before. And the speaker is going to produce a sound wave in here at a certain frequency. So the frequency is fixed to somewhere around 1,000 hertz. You're going to know what that frequency is. It'll be on the dial on the frequency generator. And as you move this piston in, you will find there are spots where the sound becomes much louder, or noticeably louder, and those are going to be antinodes, just like the maximum amplitude of the string in the previous experiment. And so you're going to have antinodes all along here. You're going to have antinodes and nodes in between, antinodes and nodes, antinodes and nodes. And actually, because this end is open and not closed, the end of this tube is basically an antinode. And of course, this end is closed because there's a piston there, and so that's going to be a node. So you don't care about all that stuff. You just want to measure the distance between antinodes or the distance between nodes, and you know that those distances are a half a wavelength. So you can decide whether to measure the quiet spots, which I think is kind of hard, or the loudest spots. I think that's the way you want to go. So measure the antinodes where it's loudest. So as you push this in, you'll find a bunch of antinodes, 3, 4, 5, 6, 7, 8, whatever antinodes, depending on somewhat on the frequency you use and the speed of sound. Of course, we still have this formula for the speed of sound is the frequency times the wavelength. And we've chosen that frequency so that the wavelengths are, several centimeters, and you can measure them with a meter stick. Okay, so you're going to measure, I would recommend, the antinodes. And don't assume the end is an antinode. There's what are called fringing effects or end effects, and the end is not exactly an antinode. So don't count that as an antinode. Stick with the antinodes you hear between the end with the speaker and the end over here where your piston is just about out of the tube. So you get 5 or 6 or 7 or 8 of these antinodes. And we have little collars to put on the tube to mark those antinodes so you can measure them later. So you want to just go through the whole thing, put little collars where the antinodes are, and measure this distance here. The distance between those collars is going to be half a wavelength. I would recommend that you put the left end or the right end, whichever you want, of the collar, move that back and forth, have the lab partner work with you and move that back and forth until you put that collar where the left edge of the collar is at the loudest sound, ditto, 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 and then measure this distance. Okay, these are half wavelength distances. So you have 5 or 6 or 7 half wavelengths, and you can measure from here to here, and here to here, and here to here. That probably is a smart thing to do, rather than say, oh, I got 4 of these, and I'm going to measure between them, and that's 2 wavelengths. So measure each half wavelength, take an average for those half wavelengths, multiply by 2 to get the wavelength, take your frequency, which you know, and the wavelength, which you just figured out from the tube, and calculate the velocity of sound in air at today's temperature. You need today's temperature, so make sure you find a thermometer. We'll have one out for you to measure the room temperature. It's not going to change very much, but the velocity of sound in air is actually very temperature dependent. In fact, if you look at equation 5, there's various ways to write this. The velocity of sound in air is 331, that's meters per second, times the square root of 1 plus the temperature in degrees Celsius divided by 273. 273, that should sound like a familiar number to you. It's the amount by which the volume of something changes per degree and so forth. It's the basis of our absolute temperature system, which is absolute zero is 273 degrees below zero in a Celsius scale. So this is a familiar old expression from a little bit earlier in the semester. So it's very temperature dependent. It's not really very temperature dependent. There's a square root here. So and again, this has to be in Celsius. So the difference between 1 plus 20 over 273 and 1 plus 22 over 273 is not a very big difference. So you're going to get pretty much this answer. Since this is above zero, I hope it's warm enough in the room to be above zero. This is going to be something about somewhere around 340 meters per second. That's the velocity of sound at room temperature. And so we're going to calculate the velocities and compare it to the calculated velocity of sound at that temperature. So those two are your two standards of comparison. Theoretically, this is more accurate, but we'll see. You can also do the air analysis here and see how well you can locate these antinodes and do an air analysis to find out how dependable your values are, or if the discrepancy between the velocity you get here and the velocity you get here is explainable with your air analysis. That's always the name of the game. Okay, well, we'll show you how this all works in the procedure part.